Hi, everyone. My name is Ermis, and I'll be presenting this work. This is joint work with Michael Carey and Sven Seuken. We're all at the University of Zurich in the ETH AI Center. Michael is also at the Harvard School of Engineering. What's our motivation? Large online platforms have started integrating generative AI across their services, and this has started quickly replacing more traditional native content in those platforms. Those are slides taken directly out of Google's I/O keynote this year. For non-generative AI content, it's well established how to mix the user-centric part of the reply with advertisers' interests. You all know too much about this. But this has been hugely successful, at this point generating over $300 billion in revenue just for the two largest companies alone. However, the next logical question is how can we do the same? How can we mix advertiser interests with the user-centric part of the reply for generative AI content in a principled manner? What's the concrete problem that we're studying? A user issues a query to an online platform. The platform has a reference LLM, PyRef, that's responsible for generating a useful reply to the user's query. At the same time, there's a set of N other LLMs that belong to advertisers and want to influence the reply back to the user. The platform's goal is to produce a useful reply for the user, while at the same time maximizing the value generated for the advertisers. As a primer, let me give you a concrete example taken out of our experimental section. The user queries what are effective ways to learn a musical instrument online. And in the reply back to the user, our mechanism was able to suggest two very valid approaches, online music lessons, interactive learning tools, while in both of these also suggesting a related advertiser. The most related piece of work is the paper by Autobidding that was presented 1 hour ago in the amphitheater next to us. In that, the authors propose an auction where the advertisers bid on a token-by-token basis for their LLM to generate the next token each time. I've highlighted different tokens in different colors. You can think of them as simple words. Despite the great strides that they made in establishing mechanism design for large language models, their paper suffers from some quite severe limitations. For one, their mechanism is not truthful if advertisers can misreport their LLMs. Additionally, it is very unclear what properties the final output distribution that their mechanism produces follows. Finally, and most importantly, advertisers suffer from the exposure problem. Say that you are the person that actually paid for all of those tokens to be generated. And at this point, you miss the critical good, your brand. Someone else stole that token. You would actually be furious. Even worse, you got that token, but the sentence continued in that way. Our mechanism, by comparison, alleviates all of those issues. For one, it is completely truthful over its inputs. Two, it converges to the theoretically optimal distribution, and we can show that it converges very rapidly. And three, advertisers face no exposure as they always bid for full output sequences. We hide no surprises later down the line. Additionally, the application that we envision for the two mechanisms is different. This is a slide taken directly from Polstock. What they suggest is that in this Google search, at the bottom of the page, you have the native content, the useful part for the user, and at the top, you have a banner in which LLMs were mixed to co-promote to brands. Right? This is the top part only serves the advertisers, while the application that we envision is that there's only one reply being generated. And this one reply is both useful for the users and the advertisers at the same time. There's no separation. Let's start with some preliminaries. An LLM is just a mapping from sequences of token to a distribution over the next token. By recursively applying that mapping, we can produce full output sequences. with pi of y conditional on x, we denote the probability that LLM pi assigns to reply y to query x. And with r underscore I of x comma y, advertiser i's reward for this. The platform's goal is to sample the final reply from the LLM that would maximize the advertiser's expected rewards, subject to it still being close to the reference LLM. Think of ChatGPT that can generate useful replies for the user. Formally, the goal looks like this. The first part is the advertiser's expected rewards. The second part is some notion of distance from the useful LLM. Here we use KL divergence. And importantly, there is this part here. This is just a real number that allows the auctioneer to balance between more useful to the user replies and higher advertiser rewards. It turns out that it's well known that this problem has an optimal solution. This is the truly optimal LLM. It's quite cute how small it is. This also implies, if we solve for the reward function, a mapping from an LLM to the reward function that induced it. This is the reward function that induced the LLM above. Even though we have a closed form solution for the optimal LLM, there's no way of directly sampling from it. That's why you can see it shut. So the standard approach in the literature is to start with a reference LLM and perform reinforcement learning with this reward function above as the objective to try and converge it. This is the standard reinforcement learning from human feedback pipeline that over the last 3-4 years has seen great success. And the next natural question is, okay, we know what the optimal LLM looks like. We know how to get to it. Why am I still talking to you? Why don't we just do this? The answer is that advertisers change from one query to the next, depending on a variety of factors, such as the RAD budgets, the user query, the user demographic. So the optimal LLM based on this closed form solution changes from one query to the very next. And we simply cannot afford this very slow and very expensive process of LLM retraining on a per query basis. Instead, our goal is a mechanism that converges to that optimal LLM as computational resources increase, is strategy proof over its whole input space, and finally, from the user's perspective, has the same delay to produce a reply as directly querying an LLM. Let's start with our allocation. First, given the user's prompt, we generate a set of N replies from some LLM pi. Those are full replies to the user's query, and each of those requires a full LLM inference code. Then we ask each advertiser the reward for all of those candidate replies. Finally, we return each of those sequences with probability proportional to the probability that the optimal LLM would assign to that sequence. As a reminder, the optimal LLM has a closed form solution, so we can evaluate this probability, divided by the probability that that sequence was generated with the LLM that we used. And we prove in the paper that as n, the number of candidate sequences that we generate, tends to infinity, for any non-degenerate LLM that could have been used to generate those candidate sequences, and this procedure converges to the theoretically optimal distribution. The obvious choice would be to use the reference LLM itself for the generation of those candidate sequences. However, in practice, that's not such a good idea. Say you're an advertiser for Nike. You only have high values for sequences that mention your brand by name. But it is very unlikely for the reference LLM, say ChatGPT, to ever mention a brand by name. So if you were to do that, the candidate sequences that would be generated would have very low value for the advertisers because they wouldn't mention them, and thus a very low objective value for the auctioneer. So in practice, the convergence rate of the mechanism will be very slow. So what do we do to remedy this? We use a context-aware LLM for the generation of the candidate sequences that knows what advertisers participate. The job of this LLM is to bridge the gap between the part of the output space valued by the advertisers and valued by the reference LLM. In the example of online advertising, the context is try to mention and the names of all participating advertisers along with a short description for each advertiser. These descriptions should be easy to verify, but at the same time, an advertiser can optimize over them. Similar to how in sponsored search auction, an advertiser can perform search engine optimization. Let's continue with our payment rule. You can think of our mechanism, once the candidate sequences have been generated, as taking n bits from each advertiser, their value for each of the n generated candidate sequences, and outputting n numbers, the probability with which each sequence will be generated. This allocation rule is cyclic monotone, meaning that it is the subgradient of some convex function. This is a sufficient and necessary condition for the existence of Rosset payments. Rosset payments are the only payments that can make the mechanism strategical. If you want some intuition, Rosset payments and cyclic monotonicity have as a special 1D case, monotonicity and milestone payments. Additionally, under those payments, agent I's utility is this big scary equation here. The important part for us is the highlighted area. Agent I's utility only depends on the aggregate reports of everyone. Right? This is just the sum over the rewards of every participant. This means that the mechanism redistributes the utility gains from the auction equally back to all participants. So we suffer from a free riding problem. Unrelated agents to the query are incentivized to participate. As long as this utility is positive, let me participate in the auction, be truthfully, and the mechanism will give me back some utility. This reduces outcome quality because those unrelated to the query agents have participated. In the what are effective ways to learn a musical instrument online example, think of someone producing medical instruments participating. And in the limit, we reach the situation where the expected utility from participation is close to zero, and a lot of agents that are unrelated are participating. The idea is to use our one degree of freedom, this offset C to combat this. And the right value for this C is to additionally charge each agent her utility if her value for all sequences was zero. With this offset, we maintain strategy proofness, and additionally, we satisfy a property we call what you give is what you get. The utility of every agent is monotone in how well aligned her exponentiated reward function is with the interim allocation rule had she not participated in the auction. Advertisers that are better aligned with everyone else get higher utility. Additionally, the mechanism is almost individually rational, meaning that an agent with weakly or strongly positive reward for all sequences will receive weakly or strongly positive utility. Finally, let me highlight some practical considerations. The computationally most expensive part of our mechanism is the generation and evaluation of those candidate sequences. However, if you notice our mechanism definition, this is completely independent among both sequences and agents, meaning that it can be completely parallelized. So in practice, the delay from a user's perspective is the same as simply querying a single LLM once. Additionally, our mechanism is compatible with more efficient methods of performing inference or enlisting advertisers' reward functions. What's our experiment setup? We use synthetic instances. Each instance consists of a user query and two related advertisers. For the reference LLM, we use the publicly available Llama 2. For the advertiser LLMs, we use the same with the added instruction answer as if you were a creative advertiser for and the name of some advertiser. And finally, the context-aware LLM has the instruction try to mention along with a list of all advertisers and their descriptions. Let me start with our experiments. In all of our plots, in the x-axis, we have the number of candidate sequences that were generated by our mechanism. We generate sequences with two different LLMs, the reference LLM in blue and the context-aware LLM in yellow. And first, you can see that if we use the context-aware version of our mechanism, then the total advertiser reward scales rapidly with the number of generated candidate sequences. If we plot the auctioneer's revenue, the two images are identical, are a mirror image of each other. The reason is that the revenue remains about 81 to 83% of the advertisers' rewards, which I found very interesting. Is also very close to what you make in search engine optimization, in sponsor search, excuse me. Next, we plot the log probability with respect to the optimal distribution of the sequence returned by our mechanism. Additionally, with a green line, we show the log probability of returning a sequence from the theoretically optimal distribution. As you can see, the context-aware version of our mechanism converges very quickly to that distribution and almost matches it with only 20 candidate sequences. And finally, if we plot the Pearson correlation coefficient between an advertiser's reward and utility with the vanilla Rosset payments and with our offsetted Rosset payments, you can see that adding the offset causes a substantial increase in the correlation between an advertiser's reward and utility, meaning that we do empirically satisfy the what you give is what you get property. To conclude, we introduced a truthful mechanism for aggregating preference over LLM outputs. Our mechanism allows for a principal way of balancing participant rewards with divergence from a reference LLM, making it very well suited for the online advertising setting. We provably and quickly converge to the optimal LLM, generating significant value for the advertisers and revenue for the auctioneer along the way. And it's the largest step to date towards integrating advertising with LLM-generated content. Finally, I'm in the job market this year, so if you're looking for postdocs, please let me know. That's all. Thank you.